Wait a minute. So, good afternoon, everyone. Let us begin today's session. Uh, okay, so in this week, Professor Ghosh he first went over a detailed example of estimating W naught, so the gross weight of the aircraft. Okay, and then for the rest of the week, he gave a introduction or a basic understanding of how to select a aerofoil for the aircraft. Okay, he has not discussed any of the aspects in detail. Okay, so he has just shared his experiences and gave kind of idea about what are the challenges or what are the things that we look for when we are selecting an aerofoil, and also when we are designing the wing. So the wing part he has discussed very briefly, and he has given more emphasis to the aerofoil. So uh, first he has discussed what is some terminology and the considerations. So what things do we consider when selecting the aerofoil? And then he has discussed about NACA 4, 5 and 6 digit series, and then there was a broad classification of aerofoils based on their thickness and their effects on stall performance basically. So their effects on stall performance. And then he has discussed what are the different, what things do we have to change when we are going from 2D aerofoil to a wing. So first, I am going to explain this example again, okay, in case anybody has any doubts, and then I will cover these topics in brief. So as you know that it is important to estimate the weight of the aircraft, because everything else such as wing size, engine performance and structural design depend on the weight. So as you know, the total weight can be broken down into the weight of the crew, the weight of the payload, the fuel and the empty weight. So the empty weight is the structural weight. And you know that generally the weight of the crew and the payload can be found from mission requirements and aviation standards, and the other two ratios must be estimated. So weight of the fuel and the empty weight. Now one thing you know that we can write this as uh, WC plus WPL, and then we can divide by uh, so this WF we can write it like this, and WE we can write it like this, and then we can rearrange everything to get this kind of equation. Okay, so if we can find out these ratios, then we can find out the total weight. So I have in this PPT I have given some reference diagrams and tables from Raymer's book. Okay, so this in this chart, this is a chart about this is a chart about WE by W naught and W naught in the x-axis, W naught in the x-axis and WE by W naught in the y-axis. And you can see that in the x-axis it is a logarithmic scale, which means this relationship is exponential. So in this logarithmic scale they are forming straight lines, which means that this is a exponential relationship. So you can see that for various classes of aircrafts we have various lines, and generally uh, yes, so generally we can write this kind of a statistical relationship. W e by W naught equal to A W naught to the power C kVs. Okay, so for various different kinds of aircrafts, these are the values of A and C, and kVs is a variable sweep constant, which is close to 1. Generally, kVs is close to 1. kVs is used for variable sweep and also used for composite materials. Like in your aircraft, if you are using composite materials, then you have to reduce the value of kVs. But for an initial estimate, kVs can be 1. And you can see that all the values of C are negative. So this means that as the weight increases, as W naught increases, uh, the fraction of the empty weight it decreases. Okay, another thing you will see here is that let me write this again. Another thing you will see here is that the ratio We by W naught depends on W naught. Okay, so uh, this the a parameter on the left hand side is also there on the right hand side of the equation. So you will see that when we are estimating weight, we have to use some kind of a numerical algorithm to converge to the weight. Okay, because this left hand side parameter is also there on the right hand side. And these are some specific fuel consumption trends. So this is your CT, as I discussed in the uh, last week. Okay, so this is specific fuel consumption, uh, the thrust one, okay, not the power one, which is used for jet engines. And for propeller driven engines, we can convert the CBHP to CT using the formula. So these are the equivalent specific fuel consumptions, and this is Mach number. And this is a table that I have given here. So this all of these things are from Raymer's book. So some important things here are that generally, like from historical data, we know that for warm up and takeoff, the weight fraction is 0.97. For climb, it is 0.985, and for landing, it is 0.995. And then we have specific fuel consumption for various jet engines, okay, for cruise and loiter. And so these are in 1 by hour units. And for propeller airplanes, these are the specific fuel consumption. So uh, here we have two values in each cell. The first one is the CBHP and the second one is the propeller efficiency eta. And again, like for reference, I have included this slide from the previous class where I have summarized for propeller and jet engine what is the SFC, what is the range and endurance formula, and what is the ideal CL that we have to fly at to maintain, like to maximize range or endurance. Okay, so we'll use this formula in when we solve the example. So this is the example, and it is taken again from Raymer's book. So in this example, we have to design a aircraft where which consists of these segments. Okay, so it is written here that it illustrates the mission requirement for a hypothetical anti-submarine warfare aircraft. The key requirement is the ability to loiter for 3 hours at a distance of 1500 nautical miles from the takeoff point. So this section, okay, this section 3 to between 3 to 4, this is the key requirement of the aircraft. Uh, and we have a equipment weight which is assumed to weigh 10,000 pounds, and it must also have a 4-man crew which totals to 800 pounds, and the cruise velocity is 0.8 Mach. And another thing, okay, so you can see this mission requirement on a chart. So we have the warm up and takeoff phase from, so we have numbered all the phases of the flight. Okay, so now if we have from warm up to takeoff, which is from 0 to 1, and then from 1 to 2 we have a climbing phase, from 2 to 3 there is a cruising phase of 1500 nautical miles, and there is a loitering phase from 3 to 4, and then again cruise 4 to 5, and then loitering for 20 minutes, and then landing. Okay, and crew weight is 800, avionics payload is 10,000. Okay, and one more thing is that we also need to know the lift by drag ratio. So in this example you can consider that L by D max is 16. Okay, so now we'll see how to estimate the gross weight. So I have drawn the chart here again for your reference, and we also know that L by D max is 16. Okay, so first what we do is that we have to, so what we have to do is we have to estimate the weight ratios for each of the segments of the flight. Okay, so from 0 to 1, 1 to 2, 2 to 3, and then we'll multiply all the segments to get the total fuel fraction. Okay, and then we'll estimate the empty weight from historical data, and that is how we'll converge to the final takeoff weight. So for the first phase, which is warm up and takeoff, we can straight away take it from historical data, which is 0.97. So if I go back to the previous slide, you can see that for warm up and takeoff, it is 0.97. So we can straight away take this from historical data. And again, from for the climbing, we can assume 0.985. Now, one more thing is there, like when your aircraft has been designed in detail, okay, you can refine these estimates. Okay, you can refine these estimates to get a better idea, but generally these are the values. So for initial design you can consider these numbers. So as we saw that for climb we can assume 0.985 from historical data. So this phase, okay, 1 to 2. So we have done 0 to 1 and 1 to 2. Next we come to the cruise phase. So for the cruise phase, the range is 1500 nautical mile, which comes to 9,114,000 feet. Okay, so here we are converting everything into FPS units, and then we are putting it into the formula so that everything is consistent. And the specific fuel consumption is 0.5 hour. So this has been taken from the table. So for cruise and high bypass turbofan, the SFC is 0.5, which comes out to this value, okay, in 1 by seconds. Then we have the velocity, which is 0.6 Mach. So the speed of sound is 994.8 feet per second. So you multiply it to get the cruise velocity. And we know that for jet engine, so this is a jet engine, high bypass turbofan. This is a jet engine. So we know that for jet engine, when we want to maximize range, okay. So in this case, we are maximizing range. So when we want to maximize range, we fly at 0.866 of the L by D max. Okay. So here this is L by D max, and we are flying at 86%. So the chosen L by D will be this. Okay, and then we can put all of this into the formula to get the value of the weight fraction. So the formula is that so see, for jet engine range, this is the formula. You can invert this formula to get the, this is the range formula, so you can invert it to get the weight fraction. Okay, then you put all these values and you will get the weight fraction as 0.852. Next we come to the loitering phase. So this phase, okay, so we have now covered this phase and now we have to consider the loitering phase. And in the loitering phase, the endurance is given as 3 hours, which is 10,800 seconds. The SFC is 0.4 per hour, which turns out to this value in per seconds, and your L by D is 16. So we know that for loitering with a jet engine, we have to fly at L by D max. You have to fly at L by D max, and and again for high bypass turbofan for loitering, the SFC is 0.4. So then you can again put it into the formula to get okay, so the value is 0.9277, and then there is again a cruise phase, and all the parameters of this cruise phase are same. We have the same range, same SFC, same velocity, same L by D. So obviously the weight fraction is also going to be the same, which is 0.852. So we have covered till here. Then from 5 to 6 we have a loitering phase for 20 minutes. So this is similar to your fourth calculation, just your E value will be different. Okay, so you do everything and you get this value 0.9917, and for landing you can take this value from your historical data. So finally you have all the ratios, like you have W1 by W naught, W2 by W1, W3 by W2. Okay, so you have all the ratios. Now we will see how can we calculate the fuel fraction and the empty fraction from these ratios. So first what we do is we multiply all of the ratios. Okay, so we multiply all the ratios, okay, and we get W7 by W naught. Now why are we doing this? We are doing this because see, uh, right till now what we have done is we have estimated the fuel fraction for each segment of the flight, and now when we multiply them we get the fuel fraction for the entire flight. So this is the fuel fraction for the entire flight from takeoff to landing. So you can see that your aircraft will weigh approximately like 60% of its takeoff weight when it is landing. So if your landing weight, if your takeoff weight is 100 kg, okay, like this is just to give you an idea. So if your takeoff weight is 100 kg, your landing weight will be 63 kg. So like if you subtract it, then obviously like around 37 kg will be lost as fuel. So, or in other words, you will require around 37 kg of fuel. So that is what we do, like we subtract this ratio from 1, okay, but we multiply it by 6%, okay, we increase it by 6% because usually 6% is the reserve fuel and the trap fuel. Okay, so this is the fuel fraction for the entire flight, and when we subtract it, I mean not the fuel fraction, the weight fraction for the entire flight, and when I subtract it from 1, I will get the fuel fraction, but that is ignoring reserve fuel. So I multiply this fuel fraction by 6% to get the actual fuel fraction, okay, which includes the reserve fuel. So that comes out to 0.387, okay, and your we by w naught is this. Okay, so this relationship has been taken from historical data. So you can see here that your so KVS has been taken as 1. So KVS has been taken as 1 and A is 0.93. So we can go to the table and check which kind of aircraft they have considered. So you can see this is a military cargo or bomber aircraft with a value of 0.93 and C value of minus 0.07. Okay, and when you put all these values, we get this final formula. Okay, so this is your you can put it in your formula which we found out earlier, which is crew plus payload by 1 minus. Okay, so this one was 800 and your payload was 10,000. Okay, when you add these you get 10,800 in the numerator, and your fuel fraction was 0.387. You subtract it from 1 to get 0.613, and we by w naught you replace with this formula. So we get this formula. Now as I told you previously that the we by w naught, so the empty fuel fraction, it empty weight fraction, it depends on w naught itself. So you can see that we want to calculate w naught, but w naught is also there in the right hand side. So we have to like start with some estimate and then uh, perform an iterative algorithm to converge to the actual value. uh, like it is you might say that okay, w naught is over here, so we can solve for w naught, but that is not possible, because you can see that this is a exponential relation and over here this is a not exponential relation. So it is not actually possible to perform algebraic operations and solve it, so we have to use a numerical algorithm. Okay, and it has been found that like simply starting with a guess and then doing it again and again, we will get a like it converges. So so they take a starting guess of 50,000 here, so you put 50,000 over here, okay, and you see that what is the value of w naught which is coming out of this formula. Okay, so when you put 50,000 on the RHS, we find that the LHS is 61,000. Okay, so then let's take a new guess of 60,000. Okay, uh, okay, so then they take a new guess of 60,000 and they put it in W naught, and then they calculate through this formula and they get a W naught of 59,000. So you can see that when you take W naught as 50,000, you are getting a calculated W naught of 61,000, which means that we have to increase the gas. So they have increased it to 60,000. When they do it at 60,000, they get 59,000, which means that they have to decrease the guessed value. So that is how this algorithm works. Okay, so then they put 59,200 and they get this, then 59,300 for which they get this, okay, and 59,310, and for that value they get just zero point 0.4 pound of error. Okay, so the error is 0.4 pound and they are satisfied with this conversion. So the final value has been taken as 59,310. Okay, now we'll discuss about airfoil and wings. So first I will discuss the basic terminology of the aerofoil. Okay, so see, aerofoil is a type of curved surface which has been specifically designed to produce lift when like air is flowing over it. Okay, so like many things can produce lift, like if even if you put a flat plate against air, this plate will also produce lift. Okay, uh, so even a flat plate can produce lift, but an aerofoil is a special kind of curved surface which has been optimized to produce more lift. Okay, and not only lift but produce lift at low drag. So L by D is higher for a aerofoil than for a plate or some other kind of surface. So first what we do is we draw a line, okay, which connects the forward edge with the called the leading edge. Okay, so it connects the leading edge and the trailing edge. So the leading edge is the surface which faces the air, and the trailing edge is the surface from which like the it is opposite of the leading edge. So your air is coming from left hand side to right hand side. So the leading edge it faces the air, and whereas the trailing edge like the air flows over it, so it leaves the air. And then you have the chord line. The chord line is a straight line which connects the leading edge to the trailing edge. And in this drawing, okay, the chord line has been taken as horizontal and the other things have been drawn in relation to it. So this line is your chord line. And they have also drawn the direction of oncoming air. You can see that it is tilted with respect to the chord line, and this angle is known as your angle of attack alpha. Okay, now usually it is difficult to manufacture a sharp leading edge. A sharp leading edge can result in low drag, especially in case of supersonic airfoils, but it is difficult to manufacture that. So usually it's a blunt leading edge, and the leading edge has some radius which they have marked as leading edge radius. Okay, now the distance between the leading edge and the trailing edge is the chord length C. Okay, this is called the chord length and it is denoted by C. Now one thing is that usually the practical airfoils, they are not symmetrical about the chord line. Okay, so you might expect that they will be symmetrical about the chord line, but the practical airfoils, they are not of this kind. Okay, they are cambered towards one side and that increases the lift on that side. Okay, so if it is symmetrical, then at zero angle of attack this will not produce any lift because the airflow is symmetrical. Okay, but you can camber the aerofoil. Camber means curving it in one direction. So when you curve the airfoil in one direction, it produces more lift in that direction. So even at zero angle of attack, it will produce more lift upwards. So here you can see the positively cambered airfoil. So when it is cambered, then there is a line called the camber line. Okay, so there is a line called the camber line. This line is the mean of the upper surface and the lower surface. So we have this upper surface of the airfoil and the lower surface of the airfoil, and when you take the midpoint of these two surfaces, you get the mean camber line. And here you can see that the mean camber line is above the chord line, so this is a positively cambered airfoil. For a symmetric airfoil, the mean camber line and the chord line are same. They are a horizontal line. And this your distance from the upper surface to the lower surface is called the thickness. Okay, thickness of the airfoil. So this is the basic terminology, and you can see that like in the bottom figure, they have again exaggerated an airfoil shape, and they have again indicated that what is the thickness. So the thickness is this distance. Okay, now I'll continue. So what are the things that we consider when we select an aerofoil or any other kind of lifting surface? So let me draw an aerofoil. So we want CL alpha to be as high as possible. So CL alpha is the slope of this CL and alpha curve. You know this, like you know the relationship between CL and alpha. So alpha is your angle of attack and CL is the lift coefficient. So this is usually, so in this graph we have a linear portion, okay, till this point. So this angle is known as alpha stall. This angle is known as alpha stall, and from 0 alpha to alpha stall usually we have a linear relationship, so we can write it as CL naught but plus CL alpha into alpha. Okay, so we can write it like this. So we want CL alpha to be high as possible. Then what will happen is that with a small angle of attack we can create more lift, but this is not a very important thing, like this is not a very important consideration, because CL alpha is on the, like it is approximately 2 pi per radian, and like for all the airfoils, okay, it is approximately 2 pi per radian, and it is very difficult to increase this beyond this limit. So this limit has been found from thin airfoil theory. So this 2 pi per radian limit has been found from thin airfoil theory. And practically also it has been seen that it is difficult to increase the CL alpha beyond this limit. So this is not that high of a priority. Okay, now the second thing that we consider is we want to maximize the alpha stall. Okay, so if we have two aerofoils, one is like this and the other one stalls at a higher angle of attack. So we will choose the second one. We want an airfoil with a high stall angle. Then what happens is that we can uh, we can pitch it up, or we can fly at high angles of attack, and we get more margin of safety. Okay, like obviously if your stall angle is 20 degrees instead of 12 degrees, then you get 8 degrees of additional margin to fly. So we want alpha stall to be as high as possible. And next is that we want CL max to be as high as possible. Now this is obvious because your aerofoil is supposed to generate lift, and if it can generate more lift, then it is obviously better. Okay, so here you can see that this second aerofoil, it generates more lift. You say CL max is higher, so we want this to be high. Another reason is that when CL max is high, then your stall speed is also low. Okay, and again, like when your stall speed is low, then we get more margin of safety. You know that V stall is, so if your CL max is higher, your V stall is low. But one thing sir has discussed is that if your V stall is very low, then your aircraft might get affected by uh, environmental wind, okay, or gusts of air. So suppose your aircraft is flying over a hot surface, okay, it is flying at a low altitude and it passes over a hot surface like a concrete slab, then the hot air coming from below, uh, it might disturb the aircraft, okay, or there is, suppose there is a sudden wind gush, then it might disturb the aircraft if your stall speed is very low. Then again we want CD to be low, okay, so we want an airfoil to have low drag, okay, so we want the lift to be high but the drag to be low, and for this purpose sir has discussed a special kind of airfoil called laminar laminar aerofoil. So he said that like a normal aerofoil has this kind of a CL by CD curve. Okay, so a normal aerofoil has a CL-CD curve like this, but a laminar aerofoil is a special kind of aerofoil where, like for certain values of CL, your CD is even lower. Okay, CD is even lower, and uh, there is a region of there is a region of CL where CD does not practically change. Okay, so these are special low drag aerofoils, but the disadvantage is that these are difficult to manufacture and these are also difficult to maintain because like we said that even like an insect or dust particle or rain or snow, these might make the aerofoil shape ineffective. So these need high maintenance. The other thing that we want is Cmac to be low. Okay, so when an aerofoil, when air passes over an aerofoil, it generates thrust, it generates lift, it generates drag, okay, but it also generates a moment, okay, and the moment is, this is especially true for cambered aerofoils, okay, because the cambered aerofoils, they uh, force the wind down, okay, so they force the air downwards, so and that downward movement happens at the back. So because of this reason they have a negative pitching moment. Okay. So Cmac is less than 0 for cambered aerofoils. Uh, but whether positive or negative, we do not want this value to be too high. Okay, then it becomes difficult to control it. Okay, next, sir has discussed about NACA 4, 5, and 6 digit specifications. So this is your NACA's 4-digit terminology. Okay, so if you have a, so what is all these NACA aerofoils? So basically a long time ago, okay, uh, NASA, okay, so a long time ago when NASA was experimenting with aircrafts and spacecrafts, they created a large database of aerofoils and their corresponding lift and drag coefficients. Okay, like right now, suppose you have to design an aerofoil or you have to design an aircraft, you will need the values, like you will need the CL, CD, okay, values. So how will you get these values? You will have to CLCD CM also. How will you get these values? You will have to perform, you have to create, like you have to first manufacture the aerofoil, and then you will have to perform experiment in a wind tunnel facility, or you will have to perform some kind of CFT analysis, okay, simulation analysis. So so it becomes very difficult and cumbersome, but right now we have huge data sets available thanks to these aerospace agencies. So NASA has had created a large database of aerofoil shapes and their corresponding uh, properties such as CL, CD, and CM. Okay, so uh, so they have released this database in the form of these NACA aerofoils. So obviously, like the first series of aerofoils is the 4-digit aerofoils. So these are like a huge list of aerofoils and the corresponding coefficients. So when we write something like NACA 2412, what does this mean? So the first digit indicates the value of max camber in 1 by 100 of C. So in this case, the max camber, so the first digit is 2, okay. So the max camber will be 0.02 C, okay, because it is 1 by 100. The second digit, it gives the location of max camber in 1 by 10th of C. So this is 0.1 C. No, so sorry, 0.4 C. Second digit is 4, so it gives the max camber location as 0.4 C. And the third and fourth digits, it gives the max thickness in 1 by 100th of C. So the max thickness is 0.12 C. Again, like C is the chord length. So if you have a aerofoil like this, okay, your max camber is the distance between the camber line and the chord line, okay, and this value is 0.02 C. So this will be 0.02, and this value is 0.4, and maximum thickness is this value, so this is 0.12. So this is the NACA 4-digit specification. Next we have the newer series of aerofoils, which is denoted by NACA 5 digits. So for example, suppose we have some aerofoil like this 23012. Here the first digit, first you multiply by 1.5, and it gives the design lift coefficient in 1 by 10th of C. So the first digit is 2, you multiply it by 1.5, so 3 by 2, like 1.5 into 2, this gives you 3, and then you multiply it by 1 by 10, so your design lift coefficient is 0.3 C. I mean no C, but design CL is 0.3. Now second and third digits you divide by 2 to get the location of max camber in 1 by 100th of C. So second and third digit is 30. So location of max camber is 0.3 C. And the fourth and fifth digits, they give the maximum thickness in 1 by 100th of C. So the maximum thickness is 0.12 C. Okay, so then we have the newer series of aerofoils, which is denoted by 6-digit NACA 6-digit aerofoils, and the 6 series of aerofoils, they have been specifically created to reduce drag. Okay, so they are mostly like laminar aerofoils, as I've discussed before that laminar aerofoils, they have a CL by CD graph like this. Okay, they have a CL by CD graph like this. So the series of aerofoils, they are laminar aerofoils. So here the first digit is always 6, which is the series number, and the second digit is the location of minimum pressure in 1 by 10th of C. So the second digit is 5, and so This is 0.5 C, and the subscript, it denotes that the load, what is the size of this low drag region. Okay, so what is the size of this bucket? So the low drag is maintained in 1/10th above and below the design lift coefficient. So here the subscript is 1, which means that like above and below 0.1, above and below the design lift coefficient, it maintains low drag. So this is 0.1 and this is 0.1, the gap. The third digit is the design lift coefficient in 1/10th. So the third digit is 2, so your design lift coefficient is 0.2. So these levels are 0.1 and zero point 0.3. So from 0.1 to 0.3 cl, drag is very low, and the fourth and fifth digits are the maximum thickness in 1/100th of C. So it is maximum thickness is 0.18. Now you can see that the rest of the specifications, they change depending on the series that we are talking about, but the maximum thickness is always specified. Okay, because the maximum thickness is a very important parameter when selecting the aerofoil. If your aerofoil is thicker, then we can fit more fuel and more components and electronics in that space. Okay, but if your airfoil is thicker, then it will also generate more drag. So thickness is a important parameter. Now we'll discuss broad classification of aerofoils based on thickness to chord ratio. Okay, so this ratio is called T by C, which is thickness to chord. So we take the maximum. So this is maximum thickness by the chord length. So with this, we can broadly classify aerofoils into fat, fat aerofoils, thin aerofoils, and then very thin. So these are not really mathematical things. Okay, so these are more like observations. Okay, that observations that people have like noticed based on uh, wind tunnel tests or like actually flying aircrafts of these types. Okay, so these are observations. So the first type is a fat airfoil. So in a fat airfoil, T by C is more than 14%. Okay, and in this kind of aerofoil, so all of the things that sir has discussed, they are how the aerofoil stalls. Okay, so the fat aerofoil, they stall from the trailing edge. So if this is your aerofoil at a angle, the stall will occur from the trailing edge. So if this is the wind direction, so then this will be the stall region from the trailing edge. So the turbulent boundary layer, it increases with increase in angle of attack, and the separation starts from the trailing edge and moves towards leading edge as alpha increases. I will show it this again in a diagram, but basically this is your turbulent section where this thing I've drawn, and this, when you increase the angle of attack, this boundary layer separation, it happens from the back of the aerofoil, and if you keep increasing, then this separation moves towards the front. Okay, and eventually like the whole flow is separated. Okay, but in this case this is good because this results, because the loss of lift in this case is very gradual, and the pitching moment also has small changes. So with respect to loss of lift and gradual and pitching moment, this is a good kind of aerofoil because there is no abrupt loss of lift. The next class of aerofoil is thin aerofoil. Okay, over here your thickness to chord ratio is between 6 to 14%, and over here the flow separates near the nose, at very small alpha, but it immediately reattaches. And at high angle of attack, reattachment does not occur, and this causes an immediate stall and abrupt change in lift and moment coefficients. So when you have a small angle of attack, in this case, uh, the flow it separates, but it again reattaches and then it flows. Okay, so this is a turbulent region. Okay, but the rest of the flow is laminar. But at high angle of attack, what happens is, so when you increase the angle of attack, this turbulent region it increases. Okay, and you can see that this turbulent region is starting from the leading edge. So when you increase the angle of attack, this region grows and grows, and so no, wait a minute. Let us say you increase this by some more. Okay, you increase the angle of attack by some more, then you will see that it forms a bigger turbulent region, but it again reattaches. If it is below the stall angle, then the flow will again reattach. But at the stall angle, what happens is the flow doesn't reattach. So this whole region becomes turbulent. Okay, and this transition this happens very abruptly. Okay, and wait a minute. So this transition it happens very abruptly and suddenly. So that is why the aircraft immediately stalls, and there is an immediate loss of lift, and the moment coefficient also changes immediately. So this is not a good aerofoil from this perspective. And very thin aerofoil, the same thing happens. Okay, so the first 2 points are same. The last point is different. Okay, so the loss of lift is smooth, but there is a large change in pitching moment. So this is the difference between your thin aerofoil and very thin aerofoil, that the loss of lift is smooth in case of very thin aerofoil. So these are some diagrams. Okay, so the first one is your fat aerofoil. So you can see that in normal conditions the flow doesn't separate. Okay, it moves smoothly above and below the aerofoil. Then you increase it a little bit, there is a small turbulent region at the back, and as you keep increasing it, this turbulent region it grows in size. Okay, but it starts from the trailing edge, and then as you increase it even more, the region it starts from the trailing edge and it moves towards the leading edge. And in this case the pitching moment change is not very much. Okay, and the loss of lift is also gradual. Next we have the thin aerofoil. So in the thin aerofoil we have a there is a separation in the beginning. Okay, towards the leading edge only there is a separation, but the flow again reattaches, and as you increase alpha, this reattachment does not occur, and you can guess that this will be like a violent kind of thing. So this causes a sudden change in the lift coefficient and the pitching coefficient. And this one is your very thin one, and this is almost the same as the thin case. Okay, so again you have this separation bubble towards the leading edge. You have the separation bubble, and as you increase alpha, the separation bubble grows, and at some point it snaps out, like it does not reattach anymore. And in this case also your CM it changes rapidly with alpha. Okay, now one thing is that I'll discuss this conventional aerofoil and laminar airfoil. So for a conventional airfoil, here this is CL and this is CD, and CL by CD graph is like this. Okay, it is some parabolic in shape, and if you draw a tangent line from the origin, you get the best best lift by drag point. Okay. Now in case of laminar airfoil, this is specifically designed to reduce drag. And what happens is that for some portion of CL, your CD is even lower than a conventional aerofoil. So for a conventional aerofoil, you might have a graph like this. Okay, the dotted lines I have indicated. So you might have a graph like this, and you can see that this region is lower than the conventional aerofoil. So you get a best lift by drag ratio which is lower than the conventional one. But as I said that manufacturing these aerofoils and maintaining them are difficult. Okay, now after discussing about aerofoils, I also discussed about wings and what are the factors that change when we transition from aerofoils to wings. So first one is the aspect ratio. Okay, now one thing over here is that the drag coefficients over here. So remember that up till now we were discussing about aerofoils, and aerofoils are, you can consider they are either like 2D, like they're placed in a 2D universe, okay, or you have to consider that they are infinite wings. So aerofoils are assumed to be infinite wings, or they're restricted to a 2D plane. But you know that in real life, like nothing is 2D, and also nothing cannot be of infinite length. So we create this finite wings. So now we have some aerofoil, and there is some length and some breadth. Okay, so the firstly the most important factor is the aspect ratio. So the aspect ratio is defined as b square by s. So if this is the top view of your plane, then b is the wingspan, b is the wingspan, and s is your total wing surface area. So and your aspect ratio is b square by s. Okay. Now when your aspect ratio increases, it indicates longer wings. Okay. So aspect ratio increases means longer wings. So obviously you know that if your aspect ratio is infinite or something, okay, or very high, if your aspect ratio is very high, then it is going to be almost like, it is going to behave almost like an infinite wing. So it is going to behave like an aerofoil only. But if your aspect ratio is low, then it is going to behave significantly different from the aerofoil. Okay, so now we have a formula for CL alpha 3D. So CL alpha 3D, CL alpha 2D by this correction factor, and you can see that the correction factor, it depends on the aspect ratio. And this is a graph of CL versus alpha for different aspect ratios. You can see that if your aspect ratio is low, then the CL is significantly lower. But if you increase the aspect ratio, then it approaches the aspect ratio of, it approaches the lifting characteristics of the aerofoil itself. So beyond AR of 8, it is almost close to the aerofoil. So for maximum efficiency, we must design wings with aspect ratio greater than 8. Okay. Now what happens is that like in case of finite wings, we have a concept called induced drag. This concept is not there in the case of aerofoils. So at the edge of the wing we have vortices, okay, and the high pressure air from below, okay, it circulates upward, it circulates up to the top of the wing surface, and this vortex, it causes a loss in lift near the edge of the wing. So the towards the root of the wing, the lift is the same, but at the tip of the wing, the lift is drastically low. So if you have a shorter wing, like let us say you have a wing like this, which is very short. So the like up this part will be turbulent air. Okay, because of the wingtip vortices. So your lifting surface is very small in this case. Okay, lifting surface is very small, and that is why your CL is going to be much smaller than the aerofoil CL. But if your wing is very long, okay, if your wing is very long, then towards the tip there will be vortices. Okay, you cannot avoid that. So towards the tip there will be vortices, but the you get a large section of the wing which is vortex free and which generates lift at the same level as the aerofoil. So the lift CL is going to be similar to the aerofoil. So the aspect ratio, okay, and now the D or the wingspan, it is proportional to the square root of the aspect ratio, and your CL by CD, this is also proportional to the square root of the aspect ratio. The next important parameter is the thickness ratio. Thickness ratio is the same as in case of aerofoils, like it is the definition is the same, which is the maximum thickness by the chord length. So the thickness ratio, it influences the structural weight of the wing, and wait a minute. This is thickness ratio, it influences the structural weight of the wing, and it has been seen that the structural weight is proportional to 1 by root over T by C. Okay, so if T by C is your T by C is half, then the structural weight reduces by 40%, and then your wing weight, it comprises 15 to 20% of the aircraft weight. Okay, so these are some, so see, these are not really any detailed things, these are some general observations that professor has shared. Okay, and wing weight is 15 to 20% of the aircraft weight, and the T by C at root is 20 to 40% thicker than T by C at tip, and when T by C increases, we get more space for fuel, but we also get more drag and more flow separation. So if you have a very thin aerofoil, then the airflow is not very disturbed. Like you can guess these things, okay. But if you have a very thick aerofoil, then your airflow has to change direction a lot, right? So this disturbance causes more drag and more flow separation. Okay, one important thing over here is that T by C at root is more than the T by C at tip. So usually, like if this is your wing, this part is thicker than this part, because like see, this part, it has to contain more fuel, it has to generate more lift, so this part is usually thicker than this part. One more important factor for wings are the wing twist. So what happens is that, like what we think is that we'll take a aerofoil and we'll extrude it and we'll create a wing. So if this is an aerofoil, we'll stack several of these aerofoils to create a wing, right? So this is what we think, but sometimes it is better like most of the times, okay, it is better not to stack aerofoils like this, but to change the shape throughout the wing. Okay, so one thing you can do is you can twist the aerofoils. So uh, first one you attach like this, but the subsequent aerofoils you twist it a little bit and attach. Okay, so in this case, you have a high angle of incidence at the root, and you have a moderate angle of incidence midway to the wing, and you have a low angle of incidence at the tip. So you can see from this diagram that the aerofoils have been twisted and attached and created, and the wing has been created. Now why has this been done? So this has been done to improve the handling capabilities at stall. So during stall, so if you want to improve the handling capabilities uh, during stall, or to create more margin of safety during the stall regime, then you twist the wing and attach it like this. Then what happens is that suppose you are at the stall angle, since your root angle of incidence is higher, what will happen is that the root region will stall first. So this will stall first, and this will stall last. Okay, so because of this, now one more thing you have to remember is that your ailerons are located towards the tip of the wing. So these are the ailerons. These are the ailerons, and they're located towards the tip of the wing. So if your tip stalled first, okay, then you would lose roll control. Okay, or roll control might be erratic and violent. Okay, but if your root stalls first, then you still maintain aileron control because your tip has not stalled yet. Your tip has a lower angle of incidence, so the tip of the wing has not stalled yet, but the root has stalled. So this maintains control and stability of the aircraft even during a stall. One more thing that can be done with a wing is that we can sweep the wing. So instead of creating a rectangular wing like this, you can sweep the wing like this. Okay, and this improves the supersonic performance, or this prevents flow along the wing to become supersonic. Okay, so like see, aircrafts, they want to fly at higher velocities. I mean, not aircrafts, but companies and designers, they want to create faster aircrafts. But when you create, there is a limit at the speed of sound. Okay, and when you approach that limit, okay, if your aircraft is not properly designed, then there is going to be high drag. Okay, if your aircraft is not properly designed, then at high velocities what happens is that some portion of your aircraft, there is supersonic flow. Okay, so in this diagram on the right, okay, in this diagram on the right, the aerofoil is not moving at supersonic speed. Okay, the velocity is not supersonic, but what happens is that due to the flow of the air, some portion of the flow becomes supersonic. Okay, but because of this reason, so that is why it is written here bubble of supersonic flow. But because of this reason there is a shock here, and there is a boundary layer separation, and this increases the drag. Okay, so this increases the drag substantially, and that is why we must consider another number called critical Mach number. So the Mach number is a limit. Okay, like if your aerofoil is flying at Mach 1 Mach, then obviously the flow is supersonic. Okay, but even below 1 Mach, let us say your aircraft is flying at um, 0.95 mark. Okay, it is very much possible that some part of your flow is becomes supersonic. So the better number to consider is the critical Mach number, and it changes from aerofoil to aerofoil. So what has been observed is that when a wing is swept, okay, then it decreases the, I mean, it increases the critical Mach number. So you can fly closer to the speed of sound. So let us say that for a normal wing, the MCR was for zero point 0.9. Okay, like for a normal wing, if you sweep the wing, then the MCR might become 0.95. So you can fly, you get some more margin to fly faster. Okay, so this is the utility of wing sweep. Okay, now I will cover some short like exercises. The first one is that what is the total fuel weight fraction for X number of mission phases. So we have done this now. So the first phase is the first phase is 0, then we have 1, 2, and then finally X. So you remember that what we did. So we found out the ratio Wx by W naught, and then we subtract this ratio from 1 and we multiply it by 6% to get the fuel fraction. So in this case the 6% has not been considered. So over here the answer will be this one, D. So 1 minus Wx by W naught. Okay, so now moving on to the next question. So this is the next question. So which of the following is not an application of a airfoil? So like obviously aerofoil provides lift, so this is not the answer. And see, all these are not the answers. This is the second one is the answer. Okay, so an aerofoil does not provide any thrust for acceleration. The rest of the things it provides. Then which of the following is not a type of aerofoil? Symmetric camber reflex vortex. So in this case, like the vortex is not a type of aerofoil. We have a symmetric aerofoils. Symmetric aerofoils means that it is symmetric above the chord line. Then you have cambered aerofoils. Now, cambered aerofoils means that it is bent above the chord line. In It is bent above the chord line like this. Now, what is the utility of this? The utility is that cambered aerofoils, they give more lift compared to symmetric aerofoils. So usually cambered aerofoils are used. But the disadvantage is that, so in case of cambered aerofoils, your CL is more, but your CMAC is also more. Like the absolute value of CMAC, this is more, and CMAC is less than 0. So there is another kind of aerofoil called reflex aerofoil. So this is like a cambered aerofoil only, but at the very end you have a upward shaping spike kind of thing. Okay, so this one has moderate CL, but your CMAC, okay, wait. CMAC will be greater than 0. Okay. So this is a reflex aerofoil. So in case of cambered aerofoil, uh, there cannot be a plane with just the wing. Okay, you will also require a tail to stabilize it, because in case of cambered aerofoil your CMAC is less than 0, so you will require a tail to stabilize the aircraft. But if you use a reflex aerofoil, then the lift is reduced, but it is not necessary to have a tail. So you can have an aircraft like this, with just a wing and a reflex aerofoil. So this is called a flying wing configuration. Okay, so this is the next question, that for the aerofoil NACA 0012, what does the 12 signify? So we know that for all of the aerofoils, the last two digit they signify the thickness ratio. So this is the answer. So thickness ratio. So the last two digits. So in this case, the thickness thickness will be 0.12 C, where C is the chord length. Okay, so this is the next question. A choice of lower T by C will result in what, like higher CL max or higher stall angle or higher critical Mach number? So in this case, the answer is this, higher critical Mach number. So lower T by C means what? It means that the aerofoil is thinner or flatter in shape. So here your T by C is high, but if it is thinner, then your T by C is lower. Now what happens is that in case of a lower T by C, the airflow is not disturbed too much. Okay, so like, as you know that if this is your free stream velocity V infinity, when the air passes over the top, the velocity increases. Okay, so the velocity of the flow increases. Okay, so since the airflow is not disturbed a lot, this increase in velocity is also not much high. Okay, so uh, so what happens is that, like, the increase in velocity is not very high, so in this case you will have a higher critical Mach number. But if you have a thicker airfoil, your increase in velocity is very much. Okay, it is higher than this case. So let us say that in this case your V infinity was 0.8, and over here it might be 0.82. Okay, in this case it might be 0.82. There will be lesser increase in the velocity of the flow. But in the same case, for a thicker airfoil, this might be 0.85. Okay, so you get more increase in the velocity. So, and remember that if anywhere on the airfoil, if the uh, flow velocity becomes 1 Mach, then we have achieved that critical stage. Okay, so that is the critical Mach number. So if your velocity is not increasing much, then there is a lesser chance of it achieving supersonic speeds. So a lower T by C or a uh, thinner aerofoil will have a higher critical Mach number. So this is the next question, which is calculate Vstall given CL max, S and rho, and the aircraft weight weighs 1780 kg. So here you know the formula for Vstall, which is 2W by S rho CL max. So you can substitute all the values. and we have to multiply the weight with 9.81. So you get 61.726 meters per second. Okay, moving to the next one. For a cambered aerofoil, Cm not AC is what? So like up till now what I've discussed, okay, so the answer is negative. Uh, Now like for symmetric ones, obviously for symmetric it is 0. For cambered it is less than 0, and for reflex it will be more than 0. Okay, okay, so this is the same question again. Through to trim a flying wing at positive angle of attack, which of the following arrangement is done? So flying wing means that the aircraft has no tail. So the aircraft has no tail, okay, and we want to trim it at positive angle of attack. Then what kind of aerofoil is used? So we cannot use a symmetric one, okay, and we cannot use a cambered one, so we have to use the reflex aerofoil. Now this is the next question. I think this is the last question. uh, what determines the longitudinal stability of the aircraft? So you will know that let me discuss what is longitudinal lateral stability. So this is your wing and tail. So longitudinal stability deals with stability in your XZ plane. So stability along, suppose, pitch motion, okay, stability along pitch motion or movement in this plane. So your thrust, lift, drag, weight, and rotation in this plane. So this is your I think this is 5. I forgot the symbol. So this is pitch. So thrust, lift, drag, weight, and pitch, okay. So stability in these forces and moments, that is called longitudinal stability, and lateral stability will be the all the other things. So suppose your side forces, okay, side forces or rotation along this axis, okay, rotation along this axis, or it could be like yaw motion, roll motion. Yaw and roll are coupled, okay, so they are not independent. So yaw motion, roll motion, side forces, okay, these come under lateral stability. So for longitudinal stability, the position of the center of gravity is very important. So the first point which is given here, relationship of thrust to weight and drag. So this is not really very important. Okay, we know that, we only know that for cruise condition your thrust is equal to drag. Okay, but there is no other condition. Okay, or there is no other way to make the aircraft stable based on thrust and drag. Okay, and thrust and weight are also uh, related with this formula for cruise condition, and but there is no really way to connect these components to stability. The second point, okay, location of CG with respect to neutral point. So this is the answer. Okay, now what is the neutral point? The neutral point is kind of like a weighted average of all the aerodynamic centers of the tail and the wing. So you know that wing, okay, when the air flows over the wing, there is a pitching moment created. Okay, now the moment is measured with respect to some point, right? So and usually that point is taken as the quarter chord point. Okay, so with respect to this point, the moment is measured. Now when you have a wing and a tail, when you have a wing and a tail, the neutral point, it is kind of like the average of all of these lifting surfaces. Instead of a wing and a tail, you can also have a wing and a canard, or you can have a canard, a wing and a tail, three of them. Okay, the neutral point is like the average. So in this case, because of these two surfaces, your neutral point might be over here, an average in an averaged position. Okay, and the location of CG with respect to this neutral point, that is important, and your CG has to be in front of the neutral point. Okay, so CG has to be in front. If it is behind, then it creates a unstable aircraft. And if the CG is exactly at the neutral point, then it creates a neutrally stable aircraft. And then we have the third point, which is location of CG with respect to maneuvering point. So what does this mean? So what is maneuvering point? So maneuvering point is that point where, see, maneuvering point is considered when a maneuver is being done, when the aircraft is like turning or climbing. Okay, in those cases. So in all of these cases, your lift by drag, it is more than thrust by weight. Wait, this will be, so lift by drag will be more than this ratio because you're performing a maneuver and the maneuver requires additional acceleration. Okay, like if you are climbing, if your airplane is climbing, then you will require additional okay, not really climbing, but during a turn, specifically during a turn, the airplane requires more acceleration, so more thrust will be generated. I mean, not more thrust, more lift has to be generated. So maneuvering point is considered when the airplane is performing a maneuver, and when the airplane is performing a maneuver, usually like we have to hold inside the inside the airplane, we have to hold the stick. Okay, the pilot has to hold the stick to perform the maneuver, and to hold the stick at a specific position, the pilot has to apply a force. Now, maneuvering point is that point where if the CG was placed, then no stick force will be required to perform that maneuver. So, maneuvering point means no stick force required to perform the maneuver. Okay, so in this way, this is somewhat connected to the longitudinal stability of the aircraft. But when the question is asked in this sort of a way, like when the question is asked in a generic way, we usually consider that the aircraft is not performing a maneuver, or what the aircraft is doing in a stable configuration. So in that context, the second option is more correct, that location of CG with respect to neutral point. Okay, so that is all for today. So thank you for joining this session. Hmm. Okay.
Is there are they is going to use in future?
So see, if you are going to work in
Because
aviation related field, then this is going to be useful.
yeah, yeah,
So see
yeah, yeah, yeah.
this is a aircraft design course. So
Mm-hmm.
like in those industries or companies that deal with aircrafts,
Hello.
there it is going to be useful. Okay, like you know companies, right? Like DRDO, then HAL, then Boeing, Airbus, and
Yeah,
all
yeah,
these
yeah.
UAV
Mm-hmm.
companies. And
Yeah. Mm-hmm.
if you are working on fixed wing UAVs, then this is going to be useful.
Okay, okay, sir. Okay. Mhm. Hello, sir. Hello,
Yes,
sir.
yes.
Hello, sir. Yeah, I have a question regarding how to calculate this fuel consumption and weight of the fuel. There is, can you explain some regarding that?
Okay. So that was actually covered in detail in the last week. So
Okay,
you
last week.
can
Actually, I was not there at that session.
no
Mm-hmm.
you can still like visit last week's videos. Okay, videos and PPTs. Still, like I'll explain briefly. So wait.
So, sir, from where? So, from where I can get that last week videos and all? From where I can get?
You can go to your you can open the course page, and on the left you have a course outline where the week 1, week 2, week 3 is written.
Yeah, 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 yeah. Okay, okay.
And
Mm-hmm.
at the last you have problem solving session. Over there you can find.
Okay, okay. At week two, at week two and week three, there might be a last problem solving session. From there, I can get videos, na?
Hmm. Videos and PPT also.
Okay. Yeah, yeah. Mm-hmm.
So I can like still explain in short. Okay, so
Yeah, yeah, yeah. Okay.
the weight is broken down into these four categories: the crew weight,
Yeah,
payload weight, fuel weight, and empty weight. Now the crew and payload weight, they are
yeah,
specified by
yeah,
the mission requirements. Okay, so usually they are given
yeah.
like
Mm-hmm.
design a aircraft which has
Mm-hmm.
to carry 10,000 pounds. So those things you know.
Yeah,
And for fuel weight and
yeah,
empty
yeah,
weight you
yeah.
have to
Mm.
estimate. Now, empty weight is
Yeah.
estimated using historical data. So,
Mm-hmm.
you usually have a relation
Wait.
like this, okay,
Uh-huh.
logarithmic relation,
Wait.
not exponential
Yeah.
relation, and these
Yeah.
are the values for different classes of aircraft. So, depending on the class of aircrafts, you can find, okay, you can estimate the empty weight.
Yeah.
And the fuel
Yeah. Yeah.
weight, now see the fuel weight will depend on obviously like how long the mission is going to fly for, or how much distance it has to fly, okay, or how fast
Mm.
it has to go. These things will affect the fuel weight. So
Mm.
so in last class we discussed about the specific fuel consumptions. This is like this is approximately like how much, like the mileage of a car. So that is so this parameter is like that only. It's like how much fuel is consumed, uh, how
Mm.
much fuel is consumed for 1 pound of thrust or 1 horsepower of power. So that is, this is like the mileage. So and then we have these formulas for propeller engine and jet engine. Okay, we have the
Mm.
formula for range and endurance.
And
uh, so this is the
endurance.
formula. So range is how much distance and endurance is how much time.
Time.
Hmm.
Yeah.
So
Mm.
what you can do is you can invert this formula to get wi by wi minus 1. Okay, so what basically, like, you multiply, take all these terms to the left side and you take exponential. Okay, then you will get wi by wi minus 1. Okay, you can solve for this. So that, like, this will be exponential relation. Okay, and the
Mm-hmm.
all these terms like range, endurance, all these terms will be over here.
Yeah.
So if you know
Mm-hmm.
all of those
Minus
values,
one.
you can calculate this weight fraction.
Yeah. Yeah. Mm. Okay.
And like in this class also I have discussed it. Okay, I've discussed an example, like if your aircraft has to climb and then cruise and loiter for 3
Mm-hmm.
hours, then what will be the weight
Mm-hmm.
fraction for each of the sections. Okay, so like sir has also discussed this, so you can see this from many sources. So, like, usually we segment the flight profile like 0, 1, 2, 3, 4, 5, 6, and 7. So there are 7 segments here, and we calculate the weight ratio for each of the segments, like W1 by W naught, W3 by W2. So all of these weight segments have been calculated. So some of the data has been taken from uh, historical data. Okay, and some has been calculated using the formula.
Hello, sir. This
Yes, yes.
warm up and takeoff, warm up and takeoff. That is taken from historical data. That is fixed.
Yes, yes. Like, unless
Yeah.
specified, you can. So I have given it in the table. Okay. So all of these
Yeah. Yeah.
tables are from Raymer. Okay.
Acha, acha,
Raymer's
okay.
book. Okay. So uh, for warm up and takeoff, it is 0.97. For climb, it is
Mm-hmm.
0.985, and for landing, this is. So unless some other value is specified, you can take these values.
Okay. Okay. Hmm.
So then we calculate
Mm.
the weight ratios, and then
Yeah.
we multiply all of the weight ratios to get W7 by W naught. So if we multiply everything, all the terms cancel and we get W7 by W naught. And then
Mm-hmm.
we can
Yeah.
calculate the fuel fraction using this formula.
Mm-hmm. Fuel fraction. Yeah. W one minus W7.
And then when you know the fuel fraction and the empty weight, you can calculate
Mm.
W naught using this formula.
W naught is gross weight.
Yes.
Yeah, gross weight. Yeah.
Okay. So okay. So, like, that's all.
Okay, sir. Hello, sir.
Yes,
Hello.
yes.
Hello, sir. From hello, sir. Actually, I have joined the session very late. Okay,
Hmm,
so
hmm,
I could not from starting to from takeoff to landing. Can you explain that one previous page in short? In short, can you explain it in short so I can that get favorable for
hmm, hmm.
this one. Yes, this one. In shortly, can you?
So,
Yeah,
so see, the for warm up and takeoff and for climb, we take these two values from the table. Okay. Then
yeah.
we come to
Huh.
the third phase, which is the cruise phase. So the cruise phase goes
Mhm.
from 2 to 3. Okay. So
Yeah,
here the distance is given as
yeah.
1500
And
nautical mile.
little bit. Mhm.
Okay, and this value comes out to 911,400 feet.
Yeah.
Okay, so in the book everything has been done in FPS unit.
Wait.
Okay,
Yeah.
foot pound second units. So they have converted all of these values to FPS units.
Yeah.
So the range is given, and
Yeah.
C is the specific fuel consumption or the mileage, and it is taken from a table.
Paper. Yeah. Yeah. 0.51.
And when you convert it
Yeah.
to seconds, you get this.
Yeah. Into 3600. Yeah.
No, divide by 3600,
Yeah. Yeah. 3600. Yeah.
and your
And
velocity
sir,
is,
hello, sir.
yes.
This a newtometer that is converted into feet. How
No,
much
no,
from which value we have to
no, no, no. This
multiply?
is this is not Newton meter. This is nautical mile.
Nautical mile. Okay. That nautical mile. If want to convert into feet, how much? What the value that we have to convert? What is that value? Nautical mile to feet.
Uh, I don't know. Let me check.
Yeah. It's okay. I will get it.
Hmm.
I will find out. Okay, sir.
So the range and the c is given, and your velocity is zero point
Yeah.
0.6 Mach, and so
Yeah.
velocity will be zero point 0.6 into speed of sound, and speed of sound
Yeah.
is 994.8
And 0.8.
feet per second. So you get 569.9 feet per
Mm.
second. Okay, and like for cruising with a jet engine,
Mm-hmm.
your L by D should be 86% of L by D max. So here I've assumed that L by D max is 16. So the L by D will be 13.9.
Mm. Yeah.
Okay, this is for cruise. So the
Yeah.
L by D comes out to be 13.9. So then you can
Mm.
put all of these things into this formula. This is for range for a jet aircraft. This is
Yeah.
range for a jet aircraft. So you can put all of these values into this formula, and you get W3 by W2 as 0.852.
Okay. Okay. W3 by W2. No. Okay.
Hmm.
RC. Okay. Mm.
Okay, now see from 2 to 3 and from 4 to 5. 2 to 3 and 4 to
Mm.
5, all the parameters are the same. So for 4 to 5
Mm.
also the value is 0.852.
Exactly
Okay.
same. Okay.
Now in
Mm-hmm.
the middle you have a loitering phase. Okay. So in this case
Yeah.
your endurance is 3 hours. Okay, which you convert to seconds, and C is zero point
Yeah.
0.4, which you again convert to seconds, and L by D will be 16. So for loitering for a jet engine, maximum efficiency is at L by D max. So L by D max is 16. So L by D will be 16. And then similarly you put all of these values into the endurance formula. So this is the endurance formula. You put all those values and you get W4 by W3 as this for 0.9277.
Mm-hmm. Okay.
Okay, so that is
Mm-hmm.
there.
Yes.
Then the fifth one is the same as 3, and for sixth you again have a loitering phase. Here everything is the same, just your uh, endurance is different. It is 1200 seconds. So similarly you put it into this formula and you get W6 by W5. Okay, you get
Mm-hmm.
0.9917.
Yeah. Yeah.
And the for landing you take it from the table.
Yeah. Yeah. Mm-hmm. Landing is also given the table. Yes. Mm.
Hmm.
Ah. Yeah. Mm-hmm.
So like that is how
Um.
you calculate all of these
Yeah.
fractions. Okay, then you can multiply them to, you get all of these fractions and then you can multiply them
In
to get W7 by W
formula, no?
naught. Hmm.
W7 by W naught.
Hmm.
Mm. So we have to multiply all the values now from W1 to W naught to W7 by W naught.
Yes,
W7 by
yes,
W naught. Hello?
yes, yes. You have to multiply all of the weight fractions. So as I have
Okay.
written here.
Yeah, yeah. Mm-hmm. Okay, okay, sir. Hello, sir.
Yes, yes.
Hello,
Hmm. Hello.
hello, sir. Sir. For power, thrust into force is the calculation for power.
Thrust into velocity.
Thrust into force,
Velocity,
velocity.
velocity.
Okay.
Hmm.
Okay. Thank you. I've cleared my doubt.
Okay. There is
Hello.
there
Yeah.
is
Okay.
another session on Tuesday evening, so you can join that if you want. Okay. Or else you can see the
Tuesday.
recording also.
Okay. 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 Okay, sir. Okay. Mm-hmm. And the book you have given that, inshallah, I will go and refer. Okay, sir. Okay.
But that
Thank
is
you,
for
sir.
performance. Okay, for design, the book is Reimers.
Remers. For design, that is Remers, no?
That this book is for performance. The
Hello.
one by John Anderson, it is for performance.
Okay. Hello, sir.
Hmm.
Hello.
Yes,
Hello,
yes.
sir. Any book which ample of numericals, so that if I so that my concept might be clear. Numericals. Is there any book or any site which provide a lot of numericals, different numericals, so that I can able to understand?
Hmm. No, like I don't know.
Okay, 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 sir.
I don't know actually.
Yeah, okay, okay, sir. Okay.